Welcome to this lecture on transition metal organometallic chemistry from principles to applications. Over the last few lectures, we have been discussing an important topic, particularly an important class of transition metal organometallic chemistry. These are mainly that of transition metal carbene complexes. Now, in the last lecture, we have looked into reactivity of transition metal carbene complexes, and particularly what we had seen is that there is a difference in reactivity that is shown by Fischer carbene complexes as well as the one that is shown by Schrock carbene complexes. And in the previous lecture, we had also seen the application aspects of this kind of transition metal carbene complexes that started by looking at this nucleophilic addition reactions for Fischer type carbenes, Fischer carbene, showing nucleophilic additions reaction. We have also seen these carbene complexes showing carbene transition metal carbene complexes used as carbene transfer agents. As carbene transfer agents, and this has been done both asymmetric as well as achiral fashion. Substrates mainly for these had been olefins. We have also looked at Wittig style reactivity of these transition metal carbene complexes, and we also had seen the utility of transition metal carbene complexes in benzene reactions, where they are used for producing aromatic rings when reacted with alkyne. Now, we are going to look into this discussion from the Schrock carbene perspective, because as the Fischer carbene was showing in nucleophilic addition reactions, Schrock carbenes show electrophilic reactions, and that we are going to study that in bit more detail in this lecture. Now, transition metal carbene complexes usually reacts like metal ylides, For example, ylide, let us say phosphorus ylide, is given by the formula CH2 and that has a resonance form of P plus CH2 minus. Now, similarly, the same can be conceived of Schrock carbenes, for example, tantalum p-cyclopentadienyl methyl CH2, which can also exists in a resonance form in a structure like that of an ylide. So, what one says that in phosphorylide that phosphorus is positively charged, whereas in metal ylide, which this rock carbene, the metal is positively charged and the carbonic moiety is negatively charged in both the cases as is shown here. And because of this canonical structure of they show similar reactivity. For example, when reacted with aluminum alkyl, let us say the reaction of phosphorylides with Al2 Me6 trimethyl aluminum dimer produces PH3P CH2 Al Me3, where aluminum is negatively charged and phosphorus is positively charged. Analogous reaction with the metal ylide or transition metal carbene complex, Schrock type complex Al2 Me6, thus gives this bis Cp2 tantalum methyl CH2 Al Me3, where again we see the aluminum is negatively charged and tantalum is positively charged, similar to what we had observed in the earlier discussion. So, basically what it says that transition metal alkylidene complexes reacts like ylides or metal ylides. The parallel reactivity is shown here, where the positive charge resides at the metal and the anionic charge resides at the carbonic moiety, which then attacks the electron deficient aluminum to give this tetraalkyl aluminum species with a negative charge on aluminum, similar to that of the ylide chemistry that we are familiar with. Now, this is an interesting aspect of the reactivity of Schrock carbene, and which has found a good use in this developing a particular reagent called T-base reagent. Now, this has come out, this application has come out from this metal ylide chemistry parallel to that of the Wittig reactions that has been observed for carbene transition metal carbene complexes, and this has led to the development of T-base reagent, particularly from Schrock carbene. And this T-base reagent is seen as an alternative to Wittig's reagent, and Wittig's reagent, and we are going to see how in what way they parallel Wittig reagent and in what way they go beyond Wittig reagent. For example, the reaction of Cp2 titanium dichloride with trimethyl aluminum in toluene at 20 degrees centigrade leads to elimination of dimethyl aluminum chloride and methane, which happens by alkylation of one of the methyl, which is CH3 from the trimethyl aluminum. From that, one molecule of Me2AlCl is eliminated, resulting in the formation of this particular reagent, which is called Tibes reagent. CpCp titanium CH2 aluminum methyl and this as chlorine. Now, this is what is called Tibes reagent. Now, this when reacted with ester in presence of base gives Wittig type reaction and produces and enolated, where one can see that this CH2 moiety has come from the CH2 moiety of this Tibes reagent. Now, not only it can make enolators from esters, which indeed is a very interesting reaction and the application specific to Tibes reagent, it can also show other kinds of interesting reaction. For example, in reaction, for example, its reaction with amides, it produces enamines similar to that of the ester, where this CH2 comes and does. So, these two are very specific and interesting applications of Tibes reagents, where by olefin can be made out of amides as well as esters. Another interesting reaction of Tibes reagent is that with acid chlorides it produces enolates. The reaction with acid chlorides, it produces enolates. For example, so here too one can see that CH2 has been put onto acid chlorides. So, here is an interesting comparison that with ester it produces
Enolathers.
From esters with amides, which produces enamines, from amides, and with acid chlorides it produces enolates. So, very interesting applications of Tabbe's reagent is seen and that has developed of this Schrock kind of carbene, and Tabbe's reagent usually is formed from platinum dichloride by reaction with trimethane aluminum, which results in elimination of a methane and dimethane aluminum chloride to give this Tabbe's reagent, which is a BCP titanium CH2 AlMe2 and chloride that reacts with different substrates giving
Enolathers.
enamines and enolates depending on the reaction that it undergoes. So, this is a very nice demonstration and application of these transition metal carbene complexes, particularly in terms of their utility in organic synthesis. Now, we are going to see the mechanism of formation that is discussed over here, where of metal carbene species from Tabbe's reagent. For example, this BCP titanium CH2 Al Me2 with chlorine bridge reacts with an olefin in presence of base and minus Me2 Al Cl, which gives the carbene, and the carbene then adds on to this olefin to give this metallocycle of the type propyl, and that at 0 degree centigrade eliminates back the olefin to give the transition metal carbene intermediate which undergoes subsequent reaction. So, what it says that this Tabbe's reagent in presence of an olefin give a metallocycle which is probably the resting state, and that eliminates back the olefin to generate this important transient and highly active transition metal carbene complexes, which undergo reaction like ylides or show the reactions which are known of Tabbe's reagent. So, this gives a glimpse at how the Tabbe's reagent functions, and the important thing to remember is that these functions via transition metal carbene complexes, and that is a important, that is the active species for this kind of transformation that Tabbe's reagent undergo, and that the active species is nothing but BCP titanium double bond CH2, that is just a transition metal carbene complex of titanium. Now, with that we come to end of discussion on of these transition metal carbene complexes, and we are going to take up something more interesting to discuss, which follows from these transition carbene complexes. These are transition metal carbine complexes. And these usually are designated by CR moiety, and as we can see that in transition metal carbine complexes the carbon is sp hybridized and different from the one which we had discussed, where it was transition metal carbene complexes, where the carbon center was sp2 hybridized. And then another interesting aspect about this sp hybridized transition metal carbine complexes are that, similar to the transition metal carbene complexes, there is a metal ligand multiple bond, bonding present between the transition metal and the carbine moiety, which being the sigma and 2 pi type interaction. As a result, the carbine complexes are very strongly attached to the transition metal, and we are going to take it up in bit more details. Now, as one sees that what are the types of carbine complexes and what is their source of utility, we are going to discuss that as we proceed on this topic. Now, to begin with, we are going to look at the preparative methods available for preparing these transition metal carbine complexes. And what is interesting is that transition metal carbine complexes are prepared serendipitously. So, it was not by design that these complexes were prepared, and the first example sort of came out by accident. Transition metal carbine complexes were prepared by serendipity, and the reaction which was tried was metal CO methyl with R. This is a Fischer carbene, where M can be chromium, molybdenum, tungsten, and when this was reacted with Lewis acid BX3, where X can be chlorine, bromine, iodine, and this R is methyl, ethyl, phenyl. The purpose was to synthesize this transition metal carbene complex of the type this, where X would undergo a substitution reaction at the carbonic carbon, which actually did not occur. And instead, the product which was obtained was of this fantastic discovery of a transition metal carbine complex, where the product obtained was CR, and this is a transition metal carbine complex and contains a triple bonded metal carbine moiety, and what really has transpired is that substitution occurred substitution at trans to carbine ligand. So, instead of this X ending on the carbon over here, the X is found trans to the carbene ligand, and this carbine ligand has more pi acidic character, more pi acidic than CO. So, this is an interesting observation for the carbine ligand, that it has created a center which is more pi acidic and also has been formed by substitution opposite to the carbene ligand, which was not planned. It was initially planned that the X would end up on the carbonic center. So, with that I would like to conclude the discussion on today's lecture. What we had done is we had looked at various kinds of reactivity of transition metal carbene complexes to begin with, and in that respect we have looked at the TB's reagent and elite type chemistry that transition metal carbenes display, particularly the Strock type carbenes, and the kind of various organic products that are obtained from various organic reagents using this TB's reagent. We have also looked into that. We have looked into the mechanism of formation of active species from TB's reagent, responsible for whole lot of the TB's type elite type chemistry that we have been discussing. And with that we concluded our discussion in this lecture on transition metal carbene complexes, and looked up another interesting topic of transition metal carbine complexes. These are sp center bonded, multiply bonded, triply bonded to the transition metal. In that perspective we have looked at the synthesis of transition metal carbine complexes, in which was initially discovered by serendipitously, where they wanted to have a substitution on the heteroatom of a carbonic moiety, but the result which was obtained was that of the formation of a transition metal carbine moiety with the substitution occurring trans to it. This was a very interesting chemistry which led to a ligand which is carbine ligand, which is more pi acidic character even than that of CO. So, that is kind of also very interesting, and probably this acidity arises from the sp nature of the carbon moiety. So, with that I would like to conclude today's discussion on reactivity of transition metal carbene chemistry, as well as the preparations on transition metal carbine chemistry, and we are going to be discussing more on transition metal carbine chemistry in bit more detail from the perspective of synthesis, reactivity, and also try to understand their bonding with respect to the frontier molecular orbital involved in these moieties, and this and many more to be the topic of next lecture. Until then, goodbye. Thank you.